Hello, everyone. Welcome to the ACIT Science Podcast. I'm here with Julius Berner. Welcome to the podcast. To just give a short introduction on your background, you're currently a PhD student at the University of Vienna, where you also did your bachelor and master's degree. And your current research focuses on the mathematical analysis of deep learning at the intersection of approximation theory, statistical learning theory, and optimization. And the mathematics of deep learning is what we are going to be talking about today. Deep learning is currently on everybody's lips, and it has received a lot of attention in the last 10 years, also because of its close relationship to artificial intelligence, and it is one of the, I guess, central buzzwords in all of science currently. So I thought as a nice kind of starting question, it would be interesting to just try to get behind what is deep learning, what does it actually mean, and how does it relate to artificial intelligence?
Hello, nice to meet you first. And yeah, deep learning is, of course, nowadays in everyone's head and also deeply connected to artificial intelligence. And I'd like to quote my colleague, who is always telling me that deep learning is everything which works nowadays. And the idea is that the field of deep learning is rapidly developing, and this definition does probably not, like one definition can probably not cover all possible settings which might be regarded as deep learning nowadays. And in a recent survey paper, we defined deep learning as a collection of techniques where deep neural networks are trained with gradient-based methods, which covers arguably most of current settings.
Yeah, it's really surprising that this kind of narrow-sounding definition of neural networks with gradient-based methods has become kind of synonymous to artificial intelligence. So maybe we can still try to delineate the two a little bit and distinguish between the two.
Yeah, according to some definitions, artificial intelligence is everything which contains some amount of if conditions. So I think artificial intelligence is a very broad term. And nowadays, it's just so deeply connected to deep learning because most of the astonishing recent results are obtained by using deep neural networks. But actually, deep learning is more like a subfield of machine learning, and which is again a subfield of artificial intelligence.
I guess the cornerstone of machine learning is to have machines that actually learn. And what we usually mean by that is that we have some kind of algorithm that is training itself. So the algorithm itself is not fixed in the initial state before it is being trained or it is learning, but it's able to transform itself to learn, to fulfill a certain task. And you can make the relationship between artificial intelligence and machine learning that we found that our human intelligence is mostly defined by our ability to learn across a very wide range of tasks, for example. But in principle, we can also imagine intelligence to have a different basis, especially because like the usual or the early approaches to AI went down a completely different road, the road of symbolic AI, for example.
Exactly, yeah. And nowadays, deep learning is more like optimizing parameters based on some data, mostly a very large amount of data, and not about hard-coded rules, but just really about the neural network or stochastic gradient descent, trying to find parameters which in the end explain and hopefully generalize the training data and then to the test data.
You already mentioned the review article you wrote with your group and your professor called The Modern Mathematics of Deep Learning. And this is a very pretty thorough analysis of the current state of the field, and is obviously much too detailed to talk about here in any to any satisfaction. But maybe we can start with a general idea. How can we actually approach deep learning mathematically, and what are the different angles that we can look at? And then maybe we can still try to focus down on a couple of the topics you cover in this review article and talk about them in a bit more detail.
I think to first define deep learning, which we did before, one has to go one step back even and talk about what machine learning is. So in our survey article, we defined a learning task as a problem where one is given two ingredients. So one has training data, which might be labeled, partially labeled, or unlabeled, depending on the task. And then a loss function, which measures our performance on this given task. And then the goal is to construct an algorithm which maps this training data to a model, which should perform well on the training data as measured by a loss function, but also generalize to unseen data. And because just performing well on the training data would rather be memorizing as opposed to learning. And so in deep learning, this learning algorithm is usually some variant of stochastic gradient descent. And basically the range of this algorithm, so-called hypothesis set, would be a set of neural networks, which can be represented by a given architecture. So historically, one has been looking at so-called feed-forward fully connected neural networks, where the one is basically a composition of affine linear mappings with a nonlinearity intertwined. And nowadays one has, as I said before, this broader idea of what a neural network is, and the trend goes more in the direction of differential programming, where we just have one graph in the background, which we can then use to compute exact derivatives, exact in the sense that up to floating point arithmetic. And the questions which arise in this field is, first of all, given such an architecture, what functions can be approximated by such an architecture, and what is the role of depth? Because historically one has been looking at shallow neural networks, which just are two affine linear mappings with a nonlinearity interjected. And nowadays neural networks has become deeper and deeper. And there's one main question nowadays, like what's the role of depth? And a second question is, why does stochastic gradient descent, despite the nonlinearity, non-convexity, and non-smoothness in some problems, converge to good local minima and small train loss? And even if we converge to small train loss, we have so large architectures nowadays in practice. For example, the new GPT-3 model with almost 200 billion parameters, and they're capable of memorizing random labels even. So why do they generalize so well on real-world data? And so this is what I would say the three main questions which mathematically need to be understood, and of course cannot be tackled in this generality for real-world applications, but in restricted settings, we try to find at least partial answers to this question. And in our survey article, we enumerated one couple of answers and also put a spotlight on some results and showed them in more detail.
I think there were already a couple of very important points in there. Maybe to just repaint the general scheme that you are trying to pursue with these deep learning applications. So you have a mapping of between the input data and some kind of labels or output data, and this is the mapping. You have a space of hypotheses, and you are trying to find the best hypotheses that would explain the mapping between this data distribution and the labels, for example. And in mathematical terms, you can express this as a function, and this is a function you are trying to approximate. So this is the cornerstone, is that you are trying to approximate arbitrary functions with these neural networks that then serve as arbitrary function approximators. So you are basically building up these functions by small parts that you can tune, and then try to come up with a big thing that then leads to a good explanation. Exactly. So yeah, this is kind of the first part, this approximation, and then you have the generalization that you also mentioned, which is kind of also a very surprising part of deep learning. And you also mentioned GPT-3, where you have so many parameters in your model. You have more parameters in your model, for example, than you actually have data points. So that means you open the door, naively speaking, to overfitting or these kind of general risks of not generalizing well, because you can fit randomness, and if you fit randomness, then your model loses explanatory power. basically.
Exactly.
So yeah, and yeah, maybe we can. I don't know if you have a place where you want to start. Maybe we can talk about approximation first, and then move on to other interesting aspects of deep learning.
Yeah, I think arguably approximation is one of the most well-studied parts of the deep learning pipeline. It has already been studied in the 80s and 90s. And as a result, we had various variants of the universal approximation theorem, which basically says that for a given continuous function and a given precision, there is a shallow feed-forward neural network approximating that function uniformly in a compact domain up to that precision. So basically, we find parameters for the first affine linear mapping and the second affine linear mapping, such that the resulting function approximates a given continuous function up to arbitrary precision, if and only if the activation function in between is not a polynomial. And the underlying idea is that basically same result holds for polynomials. It's called the Stone-Weierstrass theorem. And then one can show that one can approximate polynomials of arbitrary degree with neural networks by finite differences. And this is already classical research done in the 80s and 90s, where neural networks have not yet been so successful in practice. And nowadays, the question is, because neural networks are getting deeper and deeper, how can we mathematically describe that and show the benefit of depth? And in the universal approximation theorem, we don't get any rate on how many neurons we need in this hidden layer. So to what first dimension we need to project our data in order to have this universal approximation capabilities. And there are recent results showing that if one wants to get efficient approximation, one needs a certain depth. And this is basically based on the fact you have been mentioning already, that we can compose very complex functions based on simple functions, but we need this compositionality. So we need the depth, we need to compose those simple functions, and just making a network wider basically just linearly increases the complexity, whereas by composing we can exponentially increase the complexity of functions we can approximate.
You mentioned the universal approximation theorems. I remember from this whole debate with Minsky's book on the fact that shallow neural networks cannot approximate a certain set of functions, and this basically showed that shallow neural networks don't really work to a certain extent. I don't know at what point in time it was shown that if you make them deep, that they can actually approximate these kind of functions as well.
I think the Minsky paper was about just one perceptron, so just one neuron, which could not approximate the XOR.
Yeah.
And this has led to the so-called AI winter, where people have deviated from neural networks again and thought that they are not useful in practice. But I think the first universal approximation theorems, which are based on shallow networks, so for those you don't need deep networks, so 2 layers are enough, they have appeared in the late 80s.
Okay, yeah. I wasn't clear about that. Okay, with a shallow network, you can pretty much approximate any function, but you don't make any claim about the width you need, basically.
Exactly. And for efficient approximation, you might need deeper networks.
And this maybe connects nicely to the breakthroughs we saw in deep learning, that then deep learning finally became kind of got us to the point of efficiency where we could really approximate very complicated functions, but still have feasible training times.
Yeah, I think the connection just from approximation theory is still hard to draw to practice, because of course, if you make our networks more complex, it's also harder to estimate the generalization error. So basically we come to the next question, but still this gives some insight of why deep neural networks seem to be more efficient and seem to be better suited for certain tasks.
So in principle, the complexity increases with depth compared to width, but there's also a trade-off. I think you have also some kind of theorems around that in the survey.
Yeah, exactly. So in order to get optimal results, one needs to trade off the depth and the width. And there has also been established universal approximation theorems where one has like fixed width but arbitrary depth. So this also exists. And as I already said before, we can emulate a lot of approximation methods using deep ReLU networks, for example. So ReLU is the activation function which just applies the maximum between of 0 and the input, and is probably the most commonly used activation function. And using this activation function, one can show that deep neural networks can efficiently approximate very complex functions. For example, even the Weierstrass function, which is a fractal function, or very highly oscillating functions. But they can also be shown to be universal in the sense that they can emulate a lot of classical methods, meaning that neural networks are from an asymptotic viewpoint as good as, for example, finite element methods, polynomial approximation, wavelets, or Gabor frames. So they have, from approximation theory perspective, they are really universal and really powerful, but one needs this depth and this compositionality in order to get those efficient results. But basically then one needs still to explain why such complex networks, which could potentially fit very undesirable patterns, why they generalize and are so well suited for applications.
Yeah, one important thing to add here is that this universal approximation theorem also extends to recurrent neural networks, which then means that you can approximate, for example, the flow fields of differential equations with neural networks as well, and then you can also model time series data, for example. And this leads to a lot of interesting applications in the sciences, because physics is essentially the study of the dynamics of the world. So you mentioned that your research is also going in this direction. So I think we will have a couple of things to talk about there as well, because my research is also going in this direction. So yeah.
Yeah, exactly. So I'm focused on numerically solving high-dimensional partial differential equations. So models from physics by means of deep learning. And I think a very interesting point in this direction is that these underlying PDEs give us a structure which we can exploit in order to, for example, a priori know the regularity of the solution we want to approximate. So there one can really get approximation results which are relevant for practice, because we know how smooth, for example, the solution to such a PDE is, even though we don't know the solution itself. And for example, and for real world applications, of course, it's very hard to grasp the optimal solution to a learning problem.
Yeah. So now that we talked about approximation, and you mentioned in several places that generalization really also connects very strongly to this whole point, we can move on to talking about generalization and important results in that direction. Maybe also about optimization, because again, everything is kind of connected.
Yeah, I think approximation can mostly be viewed in isolation, basically, because it's just about how well can certain function class be approximated by some architecture. But optimization and generalization seem to be very intertwined and should probably be studied together. And the reason is that for sufficiently large neural networks, we can have many global minima of our empirical training problem, basically. But not all of those generalize well. So it depends on the evolution of our stochastic gradient descent if we arrive at a global minimum which generalizes also. And to talk about the convergence, for example, of stochastic gradient descent, there has been recently a line of research which looks at neural networks in the infinite width regime. So they let the width go to infinity, and then make use of basically of the law of large numbers in order to estimate how a neural network in this limit will look like. And they found out that it behaves similar to a Gaussian process. And they also found out that the evolution under gradient descent is governed by a constant deterministic kernel. So basically, neural networks can be connected to kernel machines. And this can be exploited in order to obtain convergent results, which then say that neural networks can be trained provably to zero training loss. So to find a global minimum, basically. Even if we don't go to this infinite width, so because we just have largely over-parameterized neural networks, and we can use some sort of stability in order to show that the result still holds true. But as said before, it's still questionable why even finding this global minimum leads to a good generalization performance. And one idea in this direction is that gradient descent in combination with a given architecture and a given loss function has some implicit bias. So by using gradient descent, you don't get an arbitrary model in the end. For example, for linear models, one can show that using the quadratic loss and suitable assumptions, that we converge to the solution with minimal Euclidean norm, which of course reduces the complexity of our hypothesis space of linear models and therefore allows for generalization results. And
maybe to backtrack at this point, in case there are some people not from the field that are still listening. I don't know if that makes much sense, but yeah, just to repeat that the loss landscape is basically the landscape of telling you how different or like how good the function you're approximating or the neural network architecture is predicting your labels, for example, based on the train data. And if you're optimizing, then your optimizer is moving through this landscape, and in the best case, you're trying to find the minimal loss, which means that then the training was successful and you explained the data perfectly. But that never automatically means that you then end up explaining the test data as well, because that's the data your model hasn't seen. And if you add the test data, then the loss landscape naturally changes up. And finding the minimum from the train data doesn't necessarily guarantee you in any way that it also explains the test data well, which is kind of this typical trade-off between bias and variance, and kind of the question of how am I overfitting my data or am I not overfitting my data? And this is where this whole question comes in.
Exactly. So classical statistical learning theory always depicts this U-shaped bias variance curve. So on the x-axis, we have the complexity of our models, and on the y-axis, we plot the train error and the test error. And of course, by increasing the complexity, the train error gets smaller and smaller because we can better fit the training data. And the test error in the beginning also gets smaller because our function, which we want to learn, can be better approximated by our model. But at some point, the test error goes up again. So we get this U-shaped curve because the model picks up some random fluctuations in our data and the variance increases. And then at some point, the training loss is at the interpolation threshold, so we can really achieve zero training error. And the test error, however, has been increasing again. And modern models have much more parameters, so they are beyond this interpolation threshold. We have more parameters than samples, or in other words, we can perfectly fit our samples, our training samples. And the question is, what happens in this regime? And classical statistical learning theory hasn't been talking much about this regime, and one thought that the test error just goes up even more if one increases the number of parameters. However, recent research has shown that one can decrease the test error in this overparameterized regime and decrease it even below the sweet spot of this U-shaped bias variance curve. So in some sense, it might make sense to add parameters in order to decrease the test loss. And of course, this all depends highly on the data distribution on your algorithm and on the model, and still can only be shown for very simple models. But I would say, summarizing, it tells you that interpolation does not contradict generalization, which is, I think, a very recent result, which caused rethinking of classical Bayes variance curves and learning theory in general.
It also seems to go a bit against our intuitions of how these networks actually fit data. And basically, we had this assumption that if you give it enough parameters, it will just blindly fit the data without, in quotation marks, trying to learn anything meaningful from them, because that necessarily entails some kind of dimensionality reduction to extract meaningful patterns. But the intuitions here are somewhat countered, I guess. Do you know of any good mathematical explanation, or has there been a lot of work in this direction that is trying to explain, like maybe in a more intuitive sense, why this is happening?
I think it's very hard to grasp intuitively. As you already have been saying, it's in the beginning very counterintuitive, and I think this is a very active line of research, so it's still not clear what are the really important points here. I think for neural networks, as I said already before, the implicit bias of gradient descent is very important, so that we don't end up. So of course there are global minimizers which do not generalize well, and we might end up in those, but just by using stochastic gradient descent, we avoid those and end up in minima which have nice generalization properties.
So can we linger on this point a little bit, because I'm not entirely sure yet I understood the whole idea behind this implicit bias of gradient descent. Can you maybe go into that again in a bit more detail?
Yeah, sure. So I basically explained it again in case of linear models, because there it's really established already, and from there one then tries to generalize this idea to neural networks. One has not yet gotten to this generality, but I mean, it's still very active research. And for linear models with the quadratic laws, and for overparameterized linear models, we know that because we are overparameterized, there would be a lot of solutions to our problem. So because we have more parameters than samples, so a lot of possible parameter constellation would give us zero training error. But if we apply gradient descent to this problem, and so we let the linear model be optimized by gradient descent, then we know that we will converge to the solution with minimal Euclidean norm. So that means out of all possible linear models, if we apply gradient descent, we will always end up at a model with minimal Euclidean norm. So basically this reduces the complexity of our hypothesis class. We could, in the beginning, we started with all linear models, but in the end, after applying gradient descent, we will always end up with a linear model with a small Euclidean norm, basically.
And that happens without using any regularization.
Exactly. So one could, of course, achieve similar results by penalizing the Euclidean norm, which is ridge regression or Tikhonov regularization, but this happens automatically by applying gradient descent. And of course, it gets much more complicated when we go to even deep linear models, where we stack basically affine linear mappings without any nonlinearity. But results are there, and they're basically promising that something like that also happens in the case of neural networks.
It seems unlikely that with gradient like in larger network settings, you also end up in the model with really the smallest norm, probably because you only like roam around in a specific subspace of the loss landscape.
Yeah, so I think it's not yet clear to what exactly solution we converge for deep neural networks, but it also depends a lot on the loss. So if we apply that to linear models with a logistic loss, logistic regression, then we end up with a solution with the largest margin. instead of the minimal Euclidean norm. So as I said, it's like a very intertwined between the loss, the model, and also the algorithm.
Yeah. And in your paper, you also mentioned that the fact that these very deep neural networks overcome their curse of dimensionality. In some sense, we can also in this point talk about this a little bit?
Yeah, so basically, when we apply machine learning algorithms to, for example, images, we have huge input dimensions. And one would expect that that somehow the complexity of the algorithm scales exponentially in the input dimension. But it seems like neural networks are very effective in dealing with high-dimensional input data. And there are different lines of explanation. So very famous, I would say, is the Manifold Assumption. So one assumes that the data lives in a lower dimensional manifold. I would say this is a convenient tool and has also been used to really provide rigorous approximation results mathematically. But in practice, I think it's not completely true, because it seems that the data is rather close to the manifold, because we can always add some noise and stay within the same class. And it's also not clear that the data needs to have the same smaller or intrinsic dimension at all different data points. So maybe like an improved idea would be that it's close to a family of manifolds, for example, with different intrinsic dimensions. This is one idea of how to explain that the neural networks do not suffer from the curse of dimensionality. In my research, I've also been using the PDE structure to basically show that. So we have been using the PDE and some stochastic interpretation of the PDE. And then we could use uniform Monte Carlo estimators. So Monte Carlo estimators are known not to suffer from the curse of dimensionality. And neural networks can approximate them, or emulate them, because of their compositionality, which we have been already describing before. So it's again somehow emulation of a classical method, which allows us to overcome the curse of dimensionality in this sense. And also sometimes neural networks can theoretically shown to simulate the method of characteristics, which is often used in PDE theory. And if we have such an underlying PDE structure, then this can also be used to show that they do not necessarily underlie this curse of dimensionality. Whereas classical methods, so maybe to explain a little bit more, who are based on a discretization of your input domain, they, of course, grow exponentially in the dimension, because even if you just split each dimension only in halves, we get 2 to the d many pieces in the end.
Yeah, maybe a completely different example from that I was thinking about is, for example, the MNIST data set is very widely used, where you show images of handwriting, and we're working a lot with variational autoencoders that basically also employ neural networks to find low-dimensional embeddings of certain high-dimensional data sets. And this is also something neural networks seem to be very good at, that then you can basically visualize the low-dimensional embedding space. And for example, have written numbers between 0 and 9, and then in this embedding space, you can see that they are nicely clustering after having been sent through these neural networks. So I don't know if this also factors in at this point, and can explain that basically this low dimensional manifold that the data actually is living on can be extracted by the neural network, and that makes it easier for the model to scale well.
Yeah, I think that this is also a possible line of explanation, that neural networks are so flexible that they can basically also be trained to detect certain invariances in the data, and also some lower dimensional manifold, such that we don't need this large input dimension. But as can be seen, for example, by using autoencoders, they can efficiently project data to a lower dimensional space. But then, of course, it's very easy to classify.
Yeah, and the space that they are embedded in can also be just to a degree meaningful. I think that's, especially in natural language processing, that's a very popular line of inquiry to find these embedding spaces for where the language is living in, and that then also has some meaningful geometric structure, for example, also where you can define meaningful metrics that give you a distance between words, and that can also extract some kind of concepts, like certain words occurring frequently at the same time or in the same context, for example.
Yeah, I think this has been a very interesting moment for natural language processing, where those word embeddings and later on the embeddings of transformer models have come into the game, basically, and gave something like the ImageNet moment for natural language processing, such that we can now basically use one pre-trained model or one pre-trained language embedding, which then can be fine-tuned in a lot of different tasks with astonishing performance.
Yeah, and that's also one of the really useful things, this whole idea of pre-training that we also encounter in image classification, for example, where you, because neural networks are classically, like a lot of people, I guess, think from previous times, that they are hyper specialized to specific tasks. And then you have these issues like catastrophic forgetting, for example, where you slightly tweak a network and then it completely forgets what it has learned. But I think we're slowly moving towards a state where you can basically compose different operations. And in image classification, you can, for example, use this already hugely pre-trained nets that then are doing the same thing as you can imagine the visual cortex doing, then some kind of edge detection that is very universally useful if you're looking at images of all kinds that you're trying to classify, because it doesn't matter if you're trying to classify cats and dogs or planes and cars or something, because you're always going to encounter the same kind of structures. And in natural language processing, it's basically the same, where you can always use a corpus of English language and it's always living in the same kind of space. And then if you have a specific task at hand, you can move on from there.
Yeah, that's true. So basically, neural networks have shown to be very efficient feature extractors. And I mean, then in the end, it doesn't matter what you use as a classification method. One usually uses also neural networks, but one can also just apply like a linear classification after one has like a nice embedding and factored out, for example, invariances or all different kinds of unnecessary information in the input data.
In the review paper, you're also talking about like more special architectures. I think maybe there's so many things to talk about. To backtrack a little bit, you are mathematically analyzing these networks, and we have now also talked about these more complex models and the CNNs for image classification and the transformer models. But what kind of networks is the mathematical community mostly looking at, and how can we analyze them?
Yeah, I think mathematics is a little bit lagging behind because the field is so fast developing, and we are basically mostly still analyzing plain feed-forward neural networks. And also we need some sense of what is the connection between the training data and the test data to make a statement about generalization, for example. So we often assume, or typically assume, some IID assumptions so that our training as well as the test data are independent of each other and identically distributed. And this, of course, is questionable if this holds in practice. And then that's the reason why, for example, my current research is, as I said, in solving partial differential equations, because there we can synthetically create our data ourselves. And so we can guarantee that this independence and identically distributed assumptions hold true, at least in a pseudo-random sense. And so we can basically rigorously apply statistical learning theory, and we get approximation and generalization results. But still, one needs to take into account that most of those results are asymptotic in nature and just give like a qualitative estimate that, for example, we can overcome the curse of dimensionality. but it does not yet give you any practically usable bounds on how should you select your architecture, or like how many samples exactly do you need. So it's just an upper bound, which basically underline what is seen in practice, that they can efficiently be used for high dimensional settings. But yeah, there's still a long way to go even in those restricted settings.
In terms of this, the mathematics kind of lagging behind the very fast moving applications, is there a place, do you think it's mostly like trying to explain the successes of the engineers that really just tried out a lot of things and trying to explain them after the fact? Or do you think mathematically analyzing these deep learning models is also helping us gain some new insights and tricks in how we could train them, for example, or set up our models?
I think now it's mostly still lagging behind, but what, for example, is already there is like counterexamples or lower bounds or impossibility results, which of course hold in general. And I think that there will be a synergy. So as soon as one understands the underlying mechanisms, of course, the ultimate goal of mathematics is then to further develop the algorithms and guide the applications.
So maybe at this stage, we can also move on to a bit of this whole idea of scientific machine learning, which also relates to your current research, more of the general question of how machine learning can actually help the sciences advance more specifically.
Yeah, I think one of the recent breakthroughs is, for example, AlphaFold, which can very accurately predict the folding behavior of proteins. And also here in Vienna, we have a group working on solving Schrödinger's equation and gaining insights which have not been possible before. And I think there's a very important intersection of natural sciences, machine learning, mathematics, because basically this allows to use classical specialized methods which have already been invented in those natural sciences, and then deform them or incorporate them into neural networks, which then we add this data-driven or machine learning part or aspect to the problem. And also because we now have, for example, for Schrödinger's equation, a precise understanding of the underlying model, we can also try to do rigorous mathematics in this sense. And we have sometimes even synthetic data, as I said, which then allows us to provide guarantees, or at least the goal is of providing guarantees in this direction, which of course is like very much desired in machine learning, because usually people think of machine learning as black box models, and especially natural sciences, one wants to have guarantees, but still uses this advantage of data-driven methods. I think that's the reason why I've also been working in this field, so of numerically solving PDEs, because their mathematics can really show rigorous results, but still that is highly relevant for practice.
Yeah, especially in quantum mechanics, you run into this very frequent problem of having a hard time simulating high-dimensional quantum systems. It's usually because the Hilbert spaces of your system are just growing exponentially in size. If you have, for example, a spin system, even a low-dimensional one, you will quickly run into huge computational burdens. So there's also a couple of interesting ideas in how you can use machine learning techniques, for example, to simulate the evolution of quantum systems or observables in a quantum mechanical setting. There's one paper using reservoir computers, for example, that then the machine learning, the neural network is basically responsible for representing the evolution of the wave function. And this can help you tackle otherwise computationally impossible issues, or at least it can give you an additional perspective to the numerically solved, or like the numerical approaches you currently have. I don't know if this also relates to what you are doing.
Yeah, I think from the perspective that even if we don't have yet precise guarantees, it allows for methods which just have not been possible before. So in my domain, where I solve Kolmogorov PDEs, which are, for example, used in financial engineering, because they include the highly celebrated Black-Scholes model from option pricing. If one has a lot of underlyings, so a lot of basically financial assets the option is based on, and they are somehow not independent of each other, then this is just by using classical methods impossible to solve, and one cannot get any insights of, for example, how does the model behave with respect to changes, or some sensitivity analysis for the solution manifold and some model calibration or uncertainty quantification. So this is, even if you don't have yet precise guarantees, we just enter domains which have not been possible before by using deep learning-based methods.
So I'm trying to get this right. So you have a set of PDEs in front of you, like for example these Kolmogorov PDEs, and then you are trying to numerically solve them. So you're not approximating the PDE system, for example, itself with a neural network, but then you are using it as a numerical solver.
Exactly. So in our sense, we have been solving parametric Kolmogorov PDEs. So the solution basically, in the sense of the Black-Scholes model, the solution describes the fair price of an option. And an option gives its holder the right, but not the obligation, to sell a certain underlying in the future at a given price. And we want to compute this price, but in a parametric sense. So depending on, for example, the evolution of those underlyings. So we basically solve a whole family of PDEs and get the whole solution family, and this allows us then at the end. So the training of this neural network, which then represents the solution, takes a long time. But if we once trained it, then we can readily use it to see how sensitive, for example, the solution is with respect to certain parameters. Or if we don't know some parameters, we can fit the model, and then also, so what you have been saying before, also to find out which of those families of PDEs, or which PDEs out of this family basically fits the given data. So I would say we have both of those approaches. We can solve the solution, but if we have this parametric approach, then we can also in the end calibrate the solution and find out basically which parameters are there in the real world.
And that helps you with uncertainty quantification, for example, because basically you have an ensemble of solutions and you can see how sensitive your solution is to slight fluctuations in the model.
Exactly. So one could just input a random variable as, for example, one of the coefficient, and then compute statistics like what's the mean or what's the variance of my solution, and in this direction, yeah.
Yeah, it reminds me of Bayesian approaches, for example, to recurrent neural networks as well, where you model the model parameters themselves as probability distributions, and then you basically draw a model from a prior distribution that you set, and then evolve the solution, and then you can basically have a set of solutions.
Yeah, exactly. So I've not yet taken that approach, and I've come along similar things when I was doing active learning, where one also, so active learning is basically the idea of letting a model decide which data should be labeled in order that the model benefits the most of it. And there one usually picks the data where the model is highly uncertain about it. But there one tries to get a distribution over the parameters by basically using something like Monte Carlo dropout. So one gets many models by turning on dropout during inference, or also by just training an ensemble and using that ensemble. The ensemble parameters basically is a discrete distribution over the parameter space.
Yeah, and these ensemble methods are also seemingly increasingly important in machine learning.
Yeah, but still the idea is that one would like to avoid it because of the computational burden and try to get different methods. But it seems that at least now is mostly beneficial to use an ensemble. Yeah.
That was also an interesting paper that I hopefully I'm not completely misrepresenting, that if you have these ensembles, then you can show that in the loss landscape between different minima, where the like different local minima in the loss landscape where you assume your ensembles to sit, usually these are connected by a low dimensional manifold that then is also basically a minima. So you can move between these ensembles along these curves. And this is from the loss landscape perspective, kind of a cool explanation on how you can then compare these models to each other and find basically infinitely many more quasi-optimal solutions.
Mm-hmm. Mm-hmm. Interesting. Yeah, I know similar results for single models where you can show that if you have a very overparameterized network, then one can move from your initialization to the global minimum by a path which does not increase your training loss by a lot. So basically, there is an almost only decreasing path to the global minimum, which of course then can be used to motivate why gradient descent works that well.
Yeah, that reminds me of, I'm not sure in which place in your survey you mentioned that, but a result that also reminded me a lot of the lottery ticket hypothesis, this whole idea that basically if you start, especially with a over-parameterized model, your optimal solution doesn't really move too much from the random initialization, but you basically just prune away unnecessary connections and basically find the proper subspace in your neural network, or the proper subsystem that already from random initialization is at the perfect place.
Yeah, that's true. So a lot of those neurons in the end can be omitted or pruned without hurting the performance. But the question is, like, a priori, one does not know which ones they are.
Yeah. So the point of training is basically like finding the right connections to prune, in a sense.
Exactly.
And do you mention in your paper a little bit why that is the case, or are there any hypotheses why this is the way these networks train?
So we could show one theoretical result which shows that basically by stochastic arguments one can prune a lot of parameters without losing that much of performance. But I think it's still unclear why this lottery ticket holds and like why some neurons just basically are unimportant for our prediction.
Yeah, I always found this really interesting because it corresponds to some of the ideas from neuroscience about how the brain actually learns. And the fact that we increasingly prune away many of our random connections, and there's also these ideas that basically the brain is randomly set up and we just generate a lot of random sequences, and learning and finding meaningful or learning meaningful patterns in the world just means associating these random sequences in the brain to certain meaningful patterns in the outside world. But the pattern itself doesn't need to mean anything, but it's just basically associated with a certain input output, because we have such an enormous space of mappings in the brain that it's basically pruning works better and you don't need to change anything.
Mm-hmm. Yeah, what maybe one analogy is that if one has a very large neural network, then one can show that each single neuron does not need to move far in order to optimize this network. So basically, if you have a lot of initially random neurons, then there's always like a very close global minimum. And yeah, this also shows up in, for example, random feature models where one just uses random features and then linearly optimizes them and gets quite astonishing results.
Yeah. This is again some of these intuitions we have about low-dimensional landscapes, which are the ones we live in, usually don't really hold when it comes to high-dimensional spaces.
Yeah, exactly.
There's also this paper, I'm not sure who wrote it, but it's basically this whole idea of the success of deep learning, or everyone was so surprised by the success of deep learning based on our incorrect intuitions about high-dimensional spaces, because we basically derived them from low-dimensional spaces. And this means that we always thought that all of that stuff won't work anyway, basically.
Yeah, I think this is very important to consider, that we are mainly motivated by low-dimensional visualizations we see, which are, of course, misleading. And especially this holds for this very high-dimensional loss landscape, because basically the loss landscape is the domain of the loss landscape is the number of all our parameters, so it's really high dimensional. And if we move along there using gradient descent, it seems that it's actually not so hard to optimize, because there's always like one direction where we can just decrease the loss. So there are so many directions that is very unlikely actually to end up in some local or in some bad point. Yeah.
Yeah, exactly. Even if you have 1,000 dimension, then pretty much everything is a settled point, because even if 999 of them will be minimal, then there's still the opportunity of finding one direction where you can still go down further. Yeah, maybe a bit of a digression, but when you think about mathematics, or when you learn mathematics, do you find it interesting or like necessary for yourself to get geometric intuitions, or do you think about it visually, or more like in terms of equations and formally?
I think that the geometric intuition for me personally is very important, especially if you want to come up with new ideas or just want to basically remember a result without just remembering all the details, because usually the details should come intuitively if one has the right intuition. Of course, this is not always easy to get, and it's always, or like at least a lot of times it's lacking in lectures one is listening to, because of course the streamlined version of teaching mathematics is usually just writing down very compressed proofs, and they have been like edited a lot of times, streamlined, so that just they are shorter. But of course, one does not know why this result holds, and I think this is important, and it's the reason why, for example, when beginning mathematics, I would recommend to watch 3 Blue 1 Brown's videos on YouTube, because he has very nice visualizations which then add a lot of intuition to some of the results in analysis or linear algebra.
Yeah, I can only join you in recommending these videos. Do you spend active time doing your research day, like kind of trying to just sit down and imagine things, or is it more like coming as a byproduct of just reading a lot?
Yeah, the question is if it's really always geometric intuition, because as we said, in high dimensional, it's very hard to get this geometric intuition. But somehow, I always like most about proofs is the motivation in the beginning, if there is one. Like, why should this result hold in an intuitive way? Like, what is really the idea behind the result? And this is also what we tried in our survey to somehow describe for some results. So on a high level, why does it hold? And then working out the details is of course important. And there it's also important to go line by line and equation by equation. But this is then just the, how would you say, like the work which comes there, but it's not really the thing you enjoy.
Yeah, when it comes to your own research, do you mainly like also run numerical simulations then, or do you mostly do pen and paper work?
I think it's both. So in the end, I mostly run some simulations, first of all, to validate my results, but also often to get intuition or to get an idea. So I would say it's a combination. But of course, I probably spend more time pondering about results, using pen and paper, writing on blackboards, talking to colleagues, and getting stuck in some proofs, basically.
Maybe to get a bit more into the details. So how do you, like, what kind of architectures do you then use to try to solve these PDEs? Like, how does the whole like algorithm architecture look like? That's quite fascinating.
Initially, one has been using just plain feed-forward neural networks because also the theory was built around them and they seem to work. In a recent paper, I tried to basically imitate multi-level Monte Carlo approaches. So basically just minimizing a residual. And so I used some multi-level architectures with residual connections, which of course allow for shorter paths of the gradient and for easier optimization of those. And for the loss function, for example, we are restricted by the problem setting. So we need to use the mean squared error loss because basically then we have the guarantee that at least for the not Monte Carlo approximated problem, so the real learning problem, the unique solution is really the solution to the PDE. So we have this guarantee, but then of course we discretize it and in order to solve it numerically.
And then you basically start out with some kind of ground truth time series derived from these systems that you have also generated yourself, and then try to approximate that. Yeah,
exactly. So I think it's maybe intuitive to look at the heat equation, which is also like a model which belongs to PDE, a Kolmogorov PDEs. And for them, we can basically uniformly sample our input data, and then we sample Brownian motions from this chosen input points. And then we know that the average of the Brownian motions after some time, evaluated at some terminal condition, basically gives us the solution of the PDE. Because this is like how heat diffusion basically works. So we have the average of Brownian motions and then applied to some terminal condition, which we know. So we know that the heat distribution at some time big T, and we basically then can average this and get the solution to our PDE at one single point. And for neural networks, we just make use of that. So we try to simulate, first of all, input data, which we feed into our neural network. And then as labels, we just take realizations of those Brownian motions added to the input data point. And the model then should basically provide something like a uniform Monte Carlo estimator. So basically average out, and one can, as said before, even show that the optimal solution would correspond to the solution of the PDE. And as like another, as said before, we can say that in this sense, we are in full control over the data, and we can also simulate as much data as we want. So this is like a little bit different setting than the usual machine learning tasks.
Yeah, it's kind of similar to what we are trying to do in our group, because we also have some ground truth data from dynamical systems where we also either we generate it ourselves and then also add some kind of noise inherent, like observation noise, but also noise directly into the process equations. So if we generate like from a dynamical system, that can also be something similar to what you're describing. We also add inherent noise in there, and then we use this data to learn basically a neural network to explain that data as well as possible. So following the same distribution in phase space, so they're having the same attractor geometry, for example. And this actually has quite a lot of practical implications as well. But as you rightly mentioned, moving from this artificially generated data then to real world data, in our case, more specifically neuroscience data, you run into a lot of problems that you don't have when you just have a lot of control over the data, because you necessarily have to make a lot of assumptions about like how nicely your data is distributed, and if it actually reflects the underlying system well, and if it's stationary, and following all of these assumptions.
Mm-hmm. Yeah. So what have you been observing there? Like what did you do in order to somehow transfer to real world data?
Like in principle, it can work, and these algorithms have been shown to work in real world applications as well. For example, for fMRI data or EEG data, all these kind of things, and also show that you can find meaningful explanations for certain cognitive phenomena. For example, in rats, where you can basically predict based on your model what kind of decision the rat is going to make. So if it's going to press a certain lever or another lever, for example.
Interesting. Mm-hmm.
And yeah, mentioning variational autoencoders earlier as well, this is also something that is being used quite frequently on top of these models, because you basically have a latent process that gives you the underlying dynamical system, and then you have the observation layer that can be, in neuroscientific examples, quite high dimensional and noisy. Again, it's a very simple example is just single neuron measurements, and then you have a lot of spike signals. But you usually assume if you have 500 spiking neurons that there's a lower dimensional explanation, because there's a lot of correlation structure between them. And then you also take neural networks to find that lower dimensional embedding, and then represent that as a dynamical system. And then you can use it to analyze what's actually happening in the brain. Because in the brain, we have this huge issue of having way too much data and not really knowing where to look, where the stuff that's actually interesting us is happening. So this is also why I think machine learning is such a promising tool for understanding the brain better, where there's a lot of communication between computational neuroscientists and the machine learning field. And it's also almost becoming kind of the same thing.
I see. So the problem is again that we have like too much to explore. Basically, the neural networks helps us where to look at.
Exactly, because they are somehow really good, as you mentioned earlier as well, if you have a huge input space to still extract these kind of figure out what is actually interesting.
Yeah. I think that's also why deep learning is becoming so popular also now, because we collect more and more data, and nobody can go through the data anymore except machine learning models, and they can extract a lot of information actually from that automatically.
Yeah, exactly. So maybe we can now slowly move on to higher level questions. We had a couple of those already. So how does your research day actually look like? Maybe we covered that a bit. You mentioned you do simulations, but also do a lot of pen and paper work. So we can go into that a bit more.
Yeah, exactly. So usually one comes up with some course idea, or one is motivated by some experiment or by some practical observations. And then one tries to work out the details in collaboration with colleagues and supervisor, which is largely done on whiteboards and tons of notes with pen and paper. Sometimes then one can write down intermediate results in LaTeX. But usually, while doing this already, the research question shifts a little bit, because one needs to adjust assumptions or add additional assumptions. And this is basically taking a long time. And I think I've mentioned it before, it can also be frustrating if you don't have any output for a couple of weeks, because you're just trying out new things. And in the end, you always end up at some dead end, or you cannot just connect the ideas in order to get a proof. But of course, it also has like very very fascinating moments, or when sometimes new ideas pop up in your head, and this can be really at any time, also not during work, and then one is just keen on trying it out. Mostly one fails at the beginning, but then one usually has a new idea and can at some point combine them. And I think that's the reason why I'm also happy to complement this research by numerical experiments and by coding. There's a very direct feedback loop, and one always gets some output. And basically, during my PhD, I needed to customize a lot of networks and trainers in order to be applicable to such specialized problems we have in solving numerically partial differential equations, for example, and also to execute them on large GPU clusters. And yeah, this was also a very interesting part of my PhD, basically.
Yeah, it's very interesting that kind of independent on where you come from and where you end up, like the toolkit you need as a modern day researcher, I would say, is it's kind of increasing, but also at the same time kind of moving closer together. That even though you are doing mathematics and I come from physics, and now doing neuroscience, we are all having to deal with similar questions of fine-tuning models and learning about GPU parallelization and all these kind of things. It's quite interesting.
Yeah, that's true. And I mean, my research basically is also at the intersection of computer science and mathematics and some physics already a little bit because of my partial differential equations I look at. And I think that in the future, probably a lot of collaboration will occur in those fields because, as you said, they use not only the same toolkit, but also the problems basically can be tackled from different perspectives, and in collaboration can then be solved.
You also have this nice quote on your website: if we knew what we were doing, it wouldn't be called research. That's very appropriate.
Yeah, that's basically, as already pointed out, in the beginning, you have just one course idea, but then you basically end up doing or solving different questions because the first question was just not possible to solve, or you needed to add some assumptions, or in the end it just did not work out. And that's also, I think, the very exciting part about research. So in general, for my PhD, I did not have any like very specialized topic, but we just wanted to basically numerically solve high dimensional problems using deep learning. And then on the way, we picked up different research questions because we had new ideas and we were interested in what about the approximation qualities in this setting, or what about the optimization behavior. And so I think this is very interesting, and this is a very inspiring area to do research in this field, which is so fast developing, and there's so many problems out there, and one can switch easily between theory and applications.
Yeah, and you can seemingly, if once you have learned the toolkits, it's fascinating how quickly you can switch between different problems. So you can work like an image classification on 1 second, and then on dynamical systems or these kind of things. And I mean, there's a bit of a learning curve usually, but it's also fascinating to see how much like common structure there is between all of these applications.
That's true. Yeah, I think the knowledge we gain from different fields, we can, at least in deep learning, apply to a lot of other fields. Of course, always take into account the domain knowledge and classical methods which might be incorporated, but some common architectures you find in various domains, basically.
Yeah, it's true that there's a certain risk of just machine learning or learners blasting into the field and just ignoring everything that has been done before. there might be some very valuable wisdom. And in machine learning, it's also interesting. We talked about these approximation theorems, but like the usual course of our research day is that like someone comes up with an idea, or we try something new, and then my professor comes along and said, there was this guy that tried this in the 90s already. So there's little new under the sun, or almost nothing new under the sun. And many of these methods there's also kind of a certain risk of there being this overhype and people not looking into the past anymore for inspiration and maybe.
Yeah. One often finds this flag planting. It's, I think, often called, where one just applies a method to some problem just to be the first and just to publish a paper, but without taking into account what has already been done and how this compares to classical methods. And as I said, I think it's in the future, it's very important to actually account for the classical methods again, and not only throw big networks at a problem. And especially if I want to have guarantees, one needs to take into account the theory which has already been done for such classical methods.
Yeah, also relating to this whole interpretability and explainability question. Like how do we actually manage to make these methods a bit less opaque to us, and connecting them to classical methods is probably a very good idea in many settings.
Yes. So sometimes one, I think, is now even training, for example, linear models locally on the neural network. So to locally explain what the neural network is doing, one makes use of linear models, for example.
Yeah, there's also work on dynamical systems where you're trying to locally linearize them in this Koopman operator framework. It's also just helping you if you have a linear model. And basically my group is also training piecewise linear recurrent neural networks, which exactly gives you these nice properties where you can compute a lot of the dynamical systems properties like fixed points and limit cycles analytically, and still retain that kind of nice features of the previous models while still having the expressivity of the neural networks.
Sounds great, yeah.
You also, I saw that you actually posted your paper on Reddit where it got a lot of traction. I found this quite cool to see like how science actually works in the age of the internet. So do you think is science changing like fundamentally, especially in this field?
Yeah, I see a lot of colleagues not promoting their research properly. So, I mean, we are all using social media and publish whatever we want, but we don't like try to use the internet for also making our research more visible and gaining publicity. And I think that nowadays it's very easy to publish it, for example, on archive first, and then just make a Reddit thread, let people discuss. You can engage in discussions. You get visibility, but you also get like questions. I got a lot of questions actually, and reading groups which asked me, and we had like discussion on certain topics. You get feedback, and I think this is not yet done enough in at least in mathematical research, that nowadays we can really discuss online on results. We can promote our results. We can add videos, for example. So I think it's also very important to sometimes add a short video where you have like a short summary of your results, and then people can see if they are really interested and if they want to read the paper. But I think it will change. So already at conferences like NeurIPS, they ask you to put a video online, to describe the paper, and I think there are more and more platforms where you can upload your paper, have discussions and feedback. For example, ResearchGate as well.
Yeah, and NeurIPS is also putting the entire review process online and on Open Science. So everything is public and you can actually follow the discussions and see the whole process behind it.
Yeah, exactly. And I think this also potentially removes bias and motivates to review properly and to engage in discussions.
So It's also kind of a meta question that can have a lot of different answers. Is there any advice you would give other researchers / yourself? Maybe if you could look back at the beginning of your PhD or like doing a master's or something, or also to other PhDs, because I think everyone learns their own lessons during their starting off in research and makes their own experiences. So I think I found it always very interesting to ask this question, because everyone has some other things they learned, and they all seem very valuable.
I think I would start like in reinforcement learning. So one needs a trade-off between exploration and exploitation. So one should be open to new problems, but then if one found a problem, then dive really deep, look into all the literature and discuss, and but always with this one idea of providing value to the scientific community. And sometimes one also loses oneself in unnecessary details and just does not produce or does not advance his current research, but just is lost somewhere in some details or in some rewriting. And one needs to, I think one needs to remind oneself that in the end, one would rewrite an article probably completely after a couple of years, because one is just more experienced, or because the research has shifted, or because some other results appeared. So I think this is also very good advice. And yeah, last but not least, the general advice of engaging in scientific discourse, giving talks, visiting conferences. So this helped me a lot. So I was missing them last year, basically, because also virtual conferences are nice. And I think it's good to know that they can work and people don't need to travel that much, but still it's nice to personally talk to each other, and basically then by accident there come new ideas and new discussions, and I think it's also, one should not be afraid of publishing in highly ranked journals and conferences, because the worst thing that can happen is like a decline, and then one tries somewhere else.
Yeah, and that whole idea of having seeking out the discussions and like trying to basically shape out ideas with other people together I think is something very fundamental. And maybe through COVID, it was a bit tricky to kind of keep these structures going, and maybe also it was harder to schedule this coffee break chat that you sometimes need to come up with an idea that you don't really focus on something very narrowly, but more have the space to discuss freely.
Yeah, exactly. That's also what I have been experiencing, that like really focused calls, you of course schedule and you talk about the topics, but there's missing this a little bit more relaxed discussion, which are also very important.
Yeah, definitely. So the last question I usually ask is what your favorite book is. You already mentioned that it might not be too interesting for the general audience, but I thought we can still talk about.
Yeah, so one favorite book of mine is Foundations of Learning Theory by Mori and others, which gives, I think, a very good introduction into the mathematics of machine learning and a good entry point. I already mentioned 3 Blue, 1 Brown's videos, if one is not yet so experienced in mathematics. And maybe like as a last idea, I'm currently reading a book by Viktor Frankl, because by accident I've been ending up living in the same building than he did, basically.
Oh, interesting. Yeah. Nice. Yeah. So that being said, I think it's time to wrap it up. Thanks a lot for this very interesting and sometimes very dense conversation, but I learned a lot and it was great having you.
Yeah, thanks a lot for having me. And I also hope that it was not too technical.
Yeah, I think we always need to find a trade-off.